Hi, my name is MacKenzie Hahn, and I'm going to talk today about abstract algebra's role in geometric constructability. As students, we tend to jump back and forth between different branches of mathematics. We may take an algebra course one semester, a geometry course immediately after, and then we might go back to an algebra course right after that. And so that's kind of just the typical structure of math classes. They tend to primarily focus on one topic at a time, and that can make it kind of difficult for students to identify connections between different branches. So today we are going to bridge the gap between two different types of mathematics, algebra and geometry. We're going to start by including an example of a basic high school level geometric construction using only an unmarked straight edge and a compass. This is because high school students typically don't learn the justifications behind geometric constructions, and so they wouldn't know how to prove this or why it works. And a lot of college students also don't know these justifications as well. So we're going to start by going through an example of a geometric construction. Abstract algebra can determine and demonstrate when something is constructible and when it is not. And so by the end of this presentation, we are going to show an example, and that example is going to be trisecting an angle, and we're going to show that that does not hold under the algebraic criteria for constructability. So starting with that geometric construction, we are going to bisect a given line segment AB. So given a line segment AB, we're going to place the compass at point A, and we're going to use a compass setting that is the length of AB, and we're going to draw a circle. Using that exact same compass setting, we could place the compass at point B and draw another circle. That circle is going to intersect the first one at 2 points. And from those 2 points of intersection, we can draw a line, and that line is going to bisect our given line AB at a point C. And C is the midpoint of AB. So we can use a compass and a straight edge to construct or to bisect a given line segment. Why are we able to do this? Well, we can start by drawing in the line segments AP, AQ, BP, and BQ, and we can find that they are all equal to each other because they are all radii in congruent circles. And next we can find that triangles APB and AQB are congruent by side, side, side. Both of these triangles are isosceles, so they have two side lengths that are equal length. Because both triangles share the side length AB, it follows that they're congruent by side, side, side. And from that, we can find that all of the angles that I've marked with the single arc are also going to be congruent because corresponding parts of congruent triangles are congruent. Similarly, we can find that triangles PAQ and PBQ are congruent by side, side, side for the similar justifications that we just had for the other triangles. And so we can find that the angles marked by the double arcs are also going to be congruent for the same reasons as the other triangles as well. Finally, we can find that the four inner triangles are all congruent to each other by angle side angle. And ultimately from that, it follows that we have line segment AC is congruent to the line segment BC. So therefore, we are able to bisect a line segment. Moving into the algebra part, we can find that a real number alpha is constructible if from a given line segment, we can construct a line segment of length alpha in a finite number of steps using a compass and a straight edge. And we can find that if we're given two constructible real numbers, alpha and beta, if we add, subtract, multiply, and divide those two constructible numbers, then the resulting number is also going to be constructible. And we're going to start by proving that addition and subtraction of two constructible numbers gives us another constructible number. We're going to assume that alpha and beta are constructible real numbers. And we can find that these arithmetic operations are constructible given any positive or negative values for alpha and beta, where alpha and beta are constructible. In this case, we're just going to assume that alpha and beta are positive because the case where the numbers are negative follows very similarly. So we start by drawing a line segment and labeling a point on the line A. We construct a circle with the center at A and a radius of alpha. And we can call the intersection of the line with the circle point B. Using point B, we can draw a circle centered at point B with a radius of beta. And we can label the intersection of this circle with the line points C and D. And so from the intersection of those two circles, it follows that the length of AD is alpha plus beta. So we can find that alpha plus beta is constructible given that alpha and beta are constructible real numbers. And it follows similarly that AC is equal to the line segment AB, which is alpha, minus the line segment BC, which is beta. And so we find that alpha minus beta is also constructible. Next, we can find that multiplying two constructible numbers gives us another constructible number. So without loss of generality, we are going to assume that alpha is greater than beta. And from this, we can construct a line segment OA with a length of alpha and a line L through a point O that does not contain the line segment OA. Then we can construct a circle with center at O and a radius of length 1, and that is going to intersect the line L at a point P. And finally, we can construct another circle centered at O with a radius of beta. That circle is going to intersect line L at point B. And we can draw on the line segment PA. We can construct a parallel line M through a point B that is parallel to line PM, and that line M is going to intersect the line segment OA at Q. And from that, we can find that the angles OPA and OBQ are congruent, and angle OAP and OQB are congruent. That's because corresponding angles of parallel lines are congruent. And since we have that two angle pairs are the same, we can conclude that all three angle measures in triangle OPA and triangle OBQ are congruent. All three of those angle measures are the same. And so we have that the two triangles are similar, and so their sides are proportional. We can write that 1 over alpha is equal to beta over the line segment OQ. Ultimately, we find that alpha times beta is constructible. And finally, we can find that alpha divided by beta is constructible. Creating this construction is pretty similar to the one above. The only difference is that we are drawing in this line segment BA, and we are constructing a parallel line, a parallel line M through the point P that is parallel to the line segment BA, and that line M is going to intersect OA at the point Q. Again, for similar reasoning as above, we can find that triangle OPQ and triangle OBA are similar, so their sides are proportional. That means that the line segment OQ is equal to alpha divided by beta. So we have that that is constructible as well. Moving on to a theorem, we can find that using a compass and a straight edge, we can only draw lines and circles. And so we can have the intersection of two lines, the intersection of a line and a circle, and the intersection of two circles. And the equations of the lines and the circles formed by those intersections are either going to be linear or quadratic. And because of that, we can only take the square roots. So next, we're going to show that the square root is constructible. So we're going to let alpha be positive and alpha be constructible. And so we are going to construct a line segment OA with a length of alpha. We can construct PA, which is equal to PO plus OA. And PO is going to have the length of 1. We know that we can bisect a given line segment, so we can bisect PA, and using the midpoint of PA, we can construct a circle with diameter PA. And from that, we can construct a perpendicular line to PA that intersects the point Q through a point O. And then from this, we can find that angle Q1 and Q2 are complementary, as well as angle A and angle Q2, and angle Q1 and angle P are complementary as well. And so from that, we can find that angle A is congruent to angle Q1 and angle P is congruent to angle Q2. And because we know that triangles QOP and AOQ both contain a right angle, we have that 3 angles in one triangle are equivalent to 3 angles in the other triangle. Therefore, both triangles are similar and their sides are proportional. Ultimately, we find that the line segment OQ squared is equal to alpha. So OQ has a length of the square root of alpha. Thus, the square root of alpha is constructible, given that alpha is a constructible number. And then incorporating a couple more definitions, we can find that E is an extension field of a field F. if F is a subfield of E. And so we have that since the rationals are a subfield of the reals, then the reals is an extension field of the rationals, for example. An element in a bigger field is algebraic over a smaller field if it's the root of some polynomial with coefficients in the smaller field. It's also important here to introduce an irreducible polynomial. We've already learned about that in previous classes, but just a little refresher, it's a polynomial that can't be factored into the product of two non-constant polynomials. And a simple extension is also going to be very important for the later corollary that we're going to talk about in this presentation. A simple extension is the smallest field, smallest subfield of a field E containing a field F, containing F and alpha. And so we can take an element and we can add it to a field, and it's going to be closed under the operations that make it a field. So therefore, a simple extension is a field generated by F and alpha. And so we have that every element of a simple extension can be uniquely expressed in the following form, beta. This is because since we know that this field is closed, we can add and multiply, and we can have any higher power of alpha, and it can be expressed as a linear combination of the following form, beta. If the degree of an irreducible polynomial is n, then we have a basis for that field as a vector space over F, and that's going to be the dimension of an extension. Just a couple more important definitions. If an extension field E of a field F is of finite dimension n as a vector space over F, then E is a finite extension of degree n over F. And so in the following theorem, this follows from our linear algebra course. We could find that when we are looking at vector spaces getting bigger, we can take the basis of E over F and then the basis of K over E, and ultimately that gives us the basis of K over F. Now applying this to simple extensions, if we consider the smallest field containing the rationals and the square root of A, where A is a non-square rational number, then we can find that the square root of A is going to be a root of x squared minus A, which is its irreducible polynomial. From that, we know that we can write the elements in Q adjoin the square root of A as b sub 0 plus b sub 1 times the square root of A, and b sub 0 and b sub 1 are going to be rational. As a vector space, we have that simple extension has a dimension of 2 over the rationals because its basis has 2 elements in it. However, just because we add on another square root does not mean that the dimension is always going to be 2. An example of this is when we are taking the rationals and adjoining the square root of 2 and the square root of 3 with the square root of 6 over the rationals adjoin square root of 2 and the square root of 3. Since the square root of 6 is already in our field of Q adjoin square root of 2 and adjoin square root of 3, then that's not going to change our dimension at all. Since square root of 6 is already in that field, its irreducible polynomial is going to be x minus the square root of 6. This corollary basically states that given gamma, which is constructible, we have a finite sequence of real numbers that we can add. So we can add a finite sequence of elements to a field. And that's going to give us, each time we add another finite element, that's going to give us a degree of 2. So for example, if we have Q adjoin the square root of alpha sub 1 over Q, that's going to give us a degree of 2 because we're taking a square root. If we add on another square root to that, the more square roots that we keep adding on, the more finite sequences of real numbers, then we're going to keep doubling our dimension by 2 each time. So ultimately our degree, we're going to get a degree of 2 to the power of r for some integer r that is greater than or equal to 0. So just a basic outline of this proof. We found that we can multiply, or we can add, subtract, multiply, and divide two constructible real numbers. And that's not going to increase the dimension of our extension field. If we add another square root to our field, it might already be in that field, as our example above with the square root of 6. So our dimension is not going to change. If the square root's not already in our field, however, then its polynomial expression it has degree 2, because at most the extension field is going to have an irreducible polynomial of degree 2. So each time we take a square root of something that we don't already have in our field, we're going to be doubling the dimension of the field at each step in that finite sequence of numbers. So ultimately, we can attach a finite sequence of square roots, and as a vector space, it's going to have a dimension 2r for some integer r that is greater than or equal to 0. To kind of explain that concept a little bit better, if we consider the square root of 5 plus the fourth root of 3, we're going to start with that innermost element. So if we take q adjoin the square root of 3 over q, because it is a square root, that's going to give us a degree of 2. If we kind of expand that and add on another square root, then we have q adjoin the fourth root of 3 over q adjoin square root of 3. Again, we're taking an additional square root. So that's going to give us another degree of 2 for that finite step right there. Once we add in 5, we talked about how adding in a number is not going to change the degree or the dimension at all. So in this final step here, since we are adding on another square root, again, that's going to give us another degree of 2. So overall, if we take q and we adjoin the square root of 5 plus the fourth root of 3 over q, we get 2 to the third power, which is 8, and that's just expected from our corollary. So now we're going to show that there's an example where we cannot construct something using a straight edge and a compass because it does not satisfy that corollary. We're going to start by trisecting an angle. We're going to show that 60 degrees is not an angle that can be trisected. And so before we can do this example, we need to introduce this lemma. So an angle theta can be constructed if and only if a segment of length cosine theta can be constructed. And so recall the identity cosine of 3 theta, which is equal to 4 cosine cubed theta minus 3 cosine theta. If we let theta equal 20 degrees, that means that cosine of 3 theta is equal to 1/2 because cosine of 60 is equal to 1/2. And we're going to let alpha equal cosine of 20 degrees. And so kind of substituting all of that into the identity, we get that 4 alpha cubed minus 3 alpha is equal to 1/2. So we get the polynomial f of x is equal to 8x cubed minus 6x minus 1, which has alpha as a root. And it's not hard to show that that function is irreducible over the rationals. So we have that it is the irreducible polynomial for alpha. Thus, it has a degree of 3. And alpha is not constructible since there is no such integer r where 3 is equal to 2r. And it's important to note that while this general case says that trisecting an angle is not possible, there are some cases where you can trisect an angle. Like for example, you can trisect a 90-degree angle. But since we know of at least one example, for example, this, we can't trisect a 60-degree angle, then we can say that in general, trisecting an angle is impossible. So using algebra, we can expand our further understanding of what denotes geometric constructability. We can use the intersections of lines and circles to create new points and construct rational numbers and square roots. And by taking constructible rational numbers and building extension fields and adjoining on more and more square roots, it's possible to develop extension fields of higher level dimensions from those constructible rational numbers. And like we talked about before, the structure of math classes are designed to primarily focus on a single math topic at a time or a single math branch. And so that means that we aren't able to kind of make those extensive connections that are present between different branches of math. So bridging the gap between algebra and geometry, as well as many other different fields of mathematics, has given us the power to expand and advance math into what we have today. I'd like to take some time to thank Dr. Shara for all of her help during this semester. And additionally, I would like to thank the math department for everything that you have taught me up to this point. Again, thank you so much for listening.